Okay, look, good afternoon, good morning, good evening, everyone, depending where you're at. This talk is really about, we'll have three parts. I will introduce myself and maybe share a few comments in relation to my career, which might be relevant to early career researcher. Then I'm going to talk really about what I'm passionate about, hydraulic engineering, and why I'm interested in hydraulic engineering. And then later on, David and Sean will moderate the discussion. As David mentioned at the beginning, I work in a school of civil engineering, and within the Australasian Filmmakers Society, I think only about 10 to 15% of the membership work in civil engineering. In civil engineering, fluid mechanics is typically applied to water engineering problem. And at UQ, in the School of Civil Engineering, our teaching include hydraulics, fluid mechanics, hydrology, and a key feature of our teaching of water engineering is a very strong practical teaching component with fieldworks in 2 compulsory courses and 2 advanced selective, and also laboratory practicals in some of our compulsory courses, which are possible thanks to a very relatively large and dynamic hydraulics laboratory, which is, in my opinion, the largest teaching and research hydraulics laboratory in Southern Hemisphere. Myself, I joined the University of Queensland about 30 years ago, after working for nearly 6 years in the industry. My research interests include environmental fluid mechanics, hydraulic structures, two-phase flow, and as an academic, my workload is 40-40-20. For those who are not familiar with this presentation, it means that my workload should be shared between 40% teaching, 40% research, 20% service and administration. And that sometimes surprises some people, considering that I have published or authored or edited over 20 books, including some of them that you should see in front of you. But in the next 4 or 5 slides, I would like to talk a little bit or to share with you some experience in relation to research and services. Administration and services do include voluntary contribution to learning societies and peer review. And I've been able to contribute to 3 learning societies over the last 28 years, which may include some meetings, some technical discussions, some technical workshop, organization of conferences, including the forthcoming Australasian Filmmakers Conference in Brisbane at the end of this year, but also in peer review, which is a necessity in our profession. And in the last 15 years, I've been involved as an expert reviewer for over 80 journals. And I would like to take this opportunity to encourage early career researcher, but also mid-career researcher to become more involved in learning society and in the peer review process. Moving into research, our profession academia has been hampered by an expression P, publish or perish, for more than 100 years, to the point with the recent explosion in the number of journals on predatory publishers, where we see an exponential growth on the number of publications, almost to a point whereby publication records become nearly meaningless. And we see instead a greater emphasis on research quality and research impact, in particular among academic recruitment committee and promotion committee. And there we have a conundrum, is that our research cannot have an impact if it's not published, because one cannot cite unpublished work. And the challenge in fluid mechanics and in hydraulic engineering is that our leading journals have a very long citation half-life, well in excess of 10 years, more like 15 to 20 years. It means that if you publish in 2020, you won't get some very good feedback for the citation in these journals until 2030 or 2035. Quite a challenge, especially for early career researchers. So in the next few slides, in fact, the next 4 slides, I'm going to share my own experience based upon some data, my own publication record on where to publish, what to publish, with whom to publish. First, maybe let's talk about where to publish. And we need, of course, to talk about the IF, the insipid factor, or what I like to call it, the insidious fudge factor. If I look at my publication record, I have over 1,200 papers in Google Scholar and around 500 to 600 papers in Scopus in Web of Science. And if I focus, for the next few slides are the 100 most cited paper of my own publication record. This graph shows the number of citations of this 100 most cited paper as a function of the impact factor of the place where they were published, Web of Science and Google Scholar. What you see in front of you is a nebulous, it's a cloud. And if one need to do a regression analysis, there is zero or negative correlation. Simply, the impact factor is not really relevant to early career researchers because it had been well acknowledged in the bibliometric bibliography that the impact factor is biased. And this is clearly acknowledged by Clarivat Analytics, which manage Web of Science. Of course, when you ask, look, should I publish by myself? Should I publish with a couple of co-authors? Should I publish with 10 co-workers? For my 100 most cited papers, this is the number of authors. The most left column are single author publication, and yes, I continue to publish as a single author. This year, for example, I've already published 3 journal papers as a single author. But the key message here is that my most cited works were either single authored or with one author. Publishing with multiple co-authors simply does not attract more impact on citation, in my opinion. But then one may ask, with whom would you publish? International scholar, domestic scholar, students? Again, if we looked at my 100 most cited papers, you can see here the 4 dominant categories with a couple of comments there. First, international collaborators. They are professional friends, in fact, good friends, most of them, with whom I spend a sabbatical or who came to spend a sabbatical with me. They are not necessarily the leading scholar in their field, but they are people that I respect a lot and that I enjoy to work a lot. But possibly the most important column is this one, the second column, which emphasize, in my opinion, the importance of student research, both postgraduate and undergraduate student research. But it also highlights the quality of the individual, the quality of these research students. And based upon my experience, I would say that co-authoring with international scholars, for the sake of co-authoring with international scholars, does not increase the impact of your work. So I share with you a lot of negativity, 3 slides of no-nos. Let's try to be positive. And I try to share that slide regularly with my research student and early career colleagues. First, you need to publish to have some impact. And the most cited papers are high quality research published ahead of time in well-targeted places. Maybe I should repeat this slightly differently. The highest impact research is outstanding quality work, published way before anyone else, typically 5 to 10 years before anyone else, in the right places with the right readership. But let's stop to talk about myself, and let's talk about hydraulic engineering. And I will start first by acknowledging that the following section and following slide are very closely related to a talk, a plenary keynote that I gave last year in Panama, and to which two young researchers, Sophia and Hong, contributed. And I want also to acknowledge some input from a number of other students, former students, young and not so young colleagues. What is hydraulic engineering? Hydraulic engineering is basically the science of water in motion and its interaction with its surrounding, water, sediments, with a very broad range of application beyond engineering. And the challenge is that we are dealing with a very broad range of relevant time and length scales over several orders of magnitude, typically more than 9 to 10 orders of magnitude. And this is a gigantic challenge. It's also a challenge because as professionals, we want to interact with our environment. We want to build hydraulic works across, beside, beneath hydraulic water bodies in riverine, estuarine, coastal zone. And our work usually in hydraulic engineering is aimed at 3 main purposes: water storage, water conveyance or transportation of water, and mitigation of the impact of water. for example, energy dissipation in a breakwater or mitigation of the flooding of an urbanized area. Interestingly, the development of hydraulic engineering has been very closely related with the birth of civilization, because life on our planet cannot be sustained without water. In turn, there have been superb hydraulic engineering heritage works. For example, this Roman bridge on the Gardon River in southern France. That bridge has experienced nearly 150 major floods in the last 600 years. And during its construction of about 20 years, and its operation by the Romans, nearly 300 years, it did experience major flood, and the bridge was designed with smart sediment scour mitigation structure. But it's not just a bridge. On the top, at the top of the third tier of arches, there's a water canal, an aqueduct. It's a Nîmes aqueduct, linking the township of Uzès to the city of Nîmes, in operation for 300 years, on section of the aqueduct still in use at the beginning of the 20th century. Another majestic system is the Intervalley Canal in coastal Peru, linking the Chicama and Moche River, built by the Mochica, extended by the Chimu, later reused by the Inca and the Spaniard in very harsh environment, as you can see from the picture. Possibly, the most important hydraulic works have been the underground great sewers beneath Berlin, Paris, London, which brought, in the 1850s, modern water sanitation and public health to our community, something that is basically regarded as a human right by the United Nations. But despite these success stories, there are arguments that hydraulic engineers are becoming complacent, that sometimes hydraulic engineering is too simplistic and too naive by developing some equations based upon one-dimensional, steady, monophase Newtonian flow, optimized typically for a single discharge. Let's look a little bit at this. Is it true that we are becoming complacent? When we have a river course, like for example Norman Creek in Brisbane, when a flash flood increases the discharge from 10 cubic meters per second to 120 cubic meters per second in barely 10 minutes, clearly we cannot assume the flow to be steady. Similarly, when we have these white waters in the Clyde Dam spillway in New Zealand, downstream of the bottom spillway aeration device, we have a mix of nearly 50% air, 50% water. Again, in this case, an assumption of monophase flow will be not appropriate. In January 2011, together with my good friend, Professor Richard Brown, we did some measurement in an inundated street of the city of Brisbane, and we collected sediment, typically between 10 to 50 micron in size, with concentration, suspended concentration in excess of 100 kilograms per cubic meter. With such hyper-concentrated flow, it is well known that the fluid flow will behave as a non-Newtonian fluid flow, and yet all the current flood modeling of the Brisbane River ignore this aspect. And how about optimizing a hydraulic structure for a discharge if it fails for 20% of the design discharge? In fact, we need to come back a little bit more on this. How about designing a structure for a design discharge which will become outdated at some stage? If we look in particular at spillway system, worldwide, there have been a massive re-evaluation of the discharge capacity. For example, near Brisbane, the Wivenhoe Dam was built to pass 12,000 cubic meters per second. The spillway capacity was increased to 27,000 cubic meters per second 20 years later. And right now, another 20 years later, we are talking of enlarging the discharge capacity to 50,000 cubic meters per second. Doubling the discharge capacity or the design discharge every 20 years. That's quite a fair lot. So this is one of the challenges in hydraulic engineering. We have massive challenges, and there are some that we still don't know how to solve. Reservoir sedimentation is one. And in front of you, the two top photographs in Japan and Australia show two reservoirs which become fully silted in 10 years. In 10 years. And while there have been clearly a lot of work on there, some people like Scott and Bruce, for example, who are very active on this topic, this remains and has been for more than 2,000 years a massive challenge. At the same time, I'm going to talk about two success stories. Success stories in the sense that fluid mechanics has been able to bring some new insight into this field. First, talking about self-aeration and hydraulic structure. On the left-hand side, you have a hydraulic jump at the bottom of a dam spillway, and you can see that the water surface is white and brown because of a mixing between air and water. Here, this hydraulic jump is dissipating energy at a rate of 2.1 gigawatt when I took the photograph, and that was only 10% of the design discharge. On the right-hand side, this is the Three Gorges project in China. I took this photograph from the top of the dam. And this jet has a dimension of 7 meters by 8 meters. And the velocity at the nozzle is 35 meters per second. And you can see that the water is completely white because of the mix between air and water. In hydraulic engineering, a fairly important development has been the work of Professor Cobus and Professor Wood, who have been able to show two dominant family of aeration, singular aeration, like in the hydraulic jump in this video, and interfacial aeration. But even this approximation or this approach is an oversimplification. If you look here in front of you at this slide of the entrainment in a spillway, apologies, and I hope you can still see it, I'm looking at myself. We have, of course, singular aeration right here at the entrapment point. But we also have interfacial aeration through entrainment and detrainment at the roller surface. And we have complicated interaction between entrained air bubble and turbulent structure, including bubble clustering. And in addition, the flow is not two-dimensional as illustrated by this slide. We have, in fact, very strong three-dimensional processes. Similarly, if we are looking at the flow down a spillway chute, like here, we have a complicated typology of the two-phase flow with a kind of bubbly flow structure in the bottom part of the flow. And in the upper part, it's more like a spray region with in between a very complicated intermediate region that we don't understand still. We have also some very dynamic interfacial processes with breakup, coalescence, rebound, collapse. All this being quite a challenge. From a professional engineering perspective, a key parameter are the inception of air entrainment. When does air start to take place? It's important not only in hydraulic engineering, but also in the food processing industry and in chemical engineering. On some seminal work by late Professor Alan Irvine, I've been able to show that the inception conditions are linked to the inflow turbulence with a graph first presented in a simplistic way in the 1980s and more recently presented in dimensionless form, which shows that for a water jet discharging vertically, we have an inception velocity about 5 meters per second in a pseudo-laminar flow, inception velocity dropping down to 1 meter per second in fully rough turbulent jets. But even such a development is still an approximation because more recent work have shown that the inception conditions are linked to a threshold in the tangential stress in the liquid carrier next to the free surface. In turn, one can develop some theoretical solution of the inception condition as a function of the bubble shape, bubble size, and the radius of curvature with one such simplistic solution. How does it compare with experimental data? What you have here is that the inception condition on the vertical axis as a function of the radius of curvature, with the thick line being the analytical solution on the dashed area being experimental observation. While qualitatively the agreement is reasonable, you can see that we have a much broader range of entrained bubble size than predicted. And this is something that applies not only at the inception condition, but more broadly over a wide range of flow conditions. So we are progressing, but at the same time, we still have some challenges. Physical modeling needs to be done in large size physical facility. And on the right-hand side, you see one of my former students and colleague, Dr. Gongfu Zhang, doing some experiment in a large flume using a fishing wading trousers. In some other experiments, we may have to equip our students with wetsuits. CFD modeling can bring further information, but as clearly shown by some colleagues like Fabian Bombardelli and Pierre Lubin, validation remains a weak link. There have been some interesting development in metrology, instrumentation, signal processing, signal analysis, but we are still lacking field observation. Let's look at another challenge, fish passage at road crossing. Culverts are among the most common hydraulic engineering structures. Every day, if you go to work or if you take the public transport to work, you will pass over at least half a dozen culverts. They are characterized by a very broad range of shape and design. And the picture in front of you were taken in Europe, North America, and in Australia. In the Australian context, one of the challenges is that we are dealing with a very broad range of flow conditions, from drought to gigantic flood. And most of our culverts, in their narrowest part, like for example, right here at the entrance of the culverts, will typically operate with a cross-sectional average velocity or bulk velocity, well in excess of 1.5 to 4.5 meters per second at design discharge. And I would like you to keep in mind this order of magnitude, 1.5 to 4.5 meters per second. It has been recognized for the past 4 to 5 decades that culverts affect adversely fish passage and fish migration, especially upstream fish passage, for a wide range of conditions linked to a lack of light, to perched outlets, standing wave in the inlet on outlet. And this interest or this motivation was initially linked to commercial fish species, shoots, salmons, fish which are strong swimmers with a sprint speed well in excess of 3 to 4 meters per second. But in the last 2 to 3 decades, there has been an interest for small body mass native fish species and juvenile of larger fish. And in front of you, you have a photograph of 4 Australian small native fish. And for these fish, which are typically 100 to 150 meter long maximum, with a swimming speed less than 0.3 to 0.8 meter per second, they are weak swimmers. For these fish, the excessive barrel velocity is the main hindrance. So what can we do about it? We can spend some money. And on the bottom photograph here, it's a culvert which has been retrofitted north of the Gold Coast at a cost of $130,000. That's very expensive. It's almost the cost of a brand new culvert. And in this case, they had to reduce the discharge capacity. In fact, if we look at it in a broader context, for Queensland alone, the retrofitting of the state-managed culverts, which need to be retrofitted for fish passage, at this cost, will cost the community in excess of $5 billion. That's quite a lot of money. And I think one of the problems is that we currently are working in a context with many guidelines were developed by biologists with a complete ignorance of basic engineering. And we, engineers, professional, researchers, academics, need to be much more proactive. In that context, I had the chance, together with some colleagues, to be working on fish passage in culvert for a research project that involved swimming with fish. What you see in front of you as a photograph is a small fish, 76 millimeter long, swimming upstream against the current in a channel which is 12 meter long, 0.5 meter wide. It's basically like a small culvert barrel at full scale. And hopefully you should start to see the video starting. It's a slow motion video, replay at 1/8 of the normal speed. And through the observation that we did, we made 2 discoveries, something that puzzled many people, but that we have been able to confirm many times. First of all, the small fish don't swim next to the bottom. They swim next to the sidewall and in the bottom corners, something that we presented at the Australasian Field Mechanics Conference in Perth. The second thing that you can see from this video is that this small fish is not sprinting. This small fish is swimming very slowly. It is trying to keep its energy. With another fish species, you have on the bottom graph here the trajectory of the fish, which over 15 minutes has progressed upstream by barely 4 meters. And we have observed fish which have taken anywhere between 1 minute to more than 1 hour to pass a 12-meter long channel. This result, which were obtained with initially Australian fish species, have been since confirmed with other small body mass native fish species from North America. But of course, every time we do laboratory work, one needs to query whether our laboratory work, whether in a large channel like here, or on the bottom like this tube test, typically used in biology, can be extrapolated to full scale, like this full scale culvert that we see on the left bottom of the slide. There is a classical approach, which is to perform dimensional analysis. And if one looked at dimensional analysis for a fish swimming upstream in a rectangular box culvert, we obtain a series of dimensionless relationships linking the fish swimming speed fluctuation, oxygen consumption, fish response time as a function of the location within the culvert, the fish species and the fish dimensions, the boundary condition, including the size of the culvert, and the turbulent flow properties. And we note, well, as fluid mechanics experts and mechanical engineers, that laboratory work can be extrapolated to a full-scale structure if all the key dimensionless parameters are the same model and prototype. And when we use the fish species in laboratory on at full scale, as everybody does, we need to ensure that the ratio of fish dimension to turbulent length scale and fish response time to turbulent time scale are the same. And when this implies that any small testing, like the small tube testing, are irrelevant because they cannot be extrapolated to full scale. And that is bad news. On the other hand, one could develop an analogy with sport physics. How hard is it for a fish to swim upstream? How hard is it? How much energy does the fish require to thrust itself? And particularly when we have detailed fish kinematics data, like this graph, which was presented again in Perth in 2016, we can develop some theoretical consideration which shows that the rate of work spent by the fish is directly proportional to the cube of the local velocity. And here the key word is local fluid velocity. We are no longer talking about a bulk or cross-sectional average velocity. We are talking about the local velocity. And in turn, we can understand why the fish are swimming in the side wall in the bottom corner. They are simply sinking low velocity zone, sizable low velocity zone. So in turn now, oops. Just bear with me, I seem to have a small problem. I lost control of PowerPoint. Murphy's Law. Apologies, everyone. My PowerPoint, yes, here it is. So right now, so practically our problem now come in modeling accurately the low velocity zone to ensure successful upstream fish passage. And that is quite a challenge, especially in hydraulic engineering, considering that it will require a fairly good understanding of turbulence in regions near the sidewall and in the bottom corners that were traditionally ignored in traditional hydraulic engineering. So to try to sum up a little bit, fish response to turbulence is not trivial, but is directly relevant to the design of fish-friendly structures. It requires a complete characterization of turbulence and fish kinematics, something that has rarely been done. To the best of my knowledge, there have been 3 studies doing it, and one of it is ours. Clearly, upscaling small laboratory tests is a major challenge, but using an analogy with sport physics, we can demonstrate that an accurate characterization of low velocity zone will enable us to develop physically based fish-friendly design. So let me conclude with a couple of slides. Hydraulic engineering and floods are not new. Floods of the Nile River have been recorded for 8,000 years. There have been hydraulic engineering books by Frontinus, Vitruvius, but also, importantly, Hero of Alexandria, nearly 2,000 years ago. Open channel hydraulics, truly speaking, is a fairly mature field. Most of our modern textbooks, including my own textbooks, are very closely related to lecture notes developed by Professor Bélanger and Professor Bress in the 1850s at the École des Ponts et Chaussées. But the development of cost-effective, fauna and flora friendly design adapted to multi-phase flow is clearly something brand new as we are moving into the 21st century. And as a professional engineer who continued to work on an ad hoc situation as a consultant, I have seen a shift in development in hydraulic engineering. Traditionally, we develop our design with a naive, simplistic optimization based upon one-dimensional, steady, monophase, Newtonian fluid flow, optimized for a single discharge, an approach that was very common during the 19th and 20th century, an approach which would work very well for design with a proven track record. Why make complicated if we can do simple with a proven track record? But at the same time, we see also the introduction of more advanced methods for modern design, using combined or hybrid modeling, for example, physical and CFD modeling, theoretical and fieldworks, which of course in any case require validation, something that is a very weak point, particularly in our Australian profession. Interaction between particles and turbulence is an interesting challenge. Turbulence on flora, turbulence on aquatic life. And of course, we need to optimize our design for a broad range of discharge. Let's take the last example of fish passage in culverts. We don't optimize a culvert for fish passage for one single discharge. We want fish passage to occur for a broad range of discharge, typically 95 to 98% of the time. With this, I thank you, and I will take this opportunity to invite you for the new era of the Australasian Filmmakers Conference in Brisbane. The conference will be hosted at both QUT and the University of Queensland as a hybrid format with both on-site and online participation. We have received already 340 abstracts. The call for paper will open soon, and even if you did not submit an abstract, we will consider your paper, of course, and we hope the registration to open soon. We look forward to meet you in Brisbane for the 22nd Australasian Filmmakers Conference. Thank you.
Thank you, Professor Chanson. That was a very interesting talk, covered a wide range of topics. I've got a new respect for the persistence of migrating freshwater fish now. Does anyone have any questions they'd like to ask? If you do, you can pop them into the group chat or use the hand raising icon in Zoom. Just while people are collecting their thoughts and thinking of questions, you emphasised a couple of times the importance of validation of CFD modelling in hydraulic engineering. In atmospheric and to a lesser extent ocean modelling, there are very, very standard and well accepted test cases in the literature now, which basically everyone has to run if they're exploring new sort of modelling capabilities or methods. Is there a sort of a consensus in the literature as to what tests are appropriate test cases for hydraulic simulation?
No, I'm very well aware of the validation test case available, for example, on the validation requirement, for example, put forward by the SME on the AIAA. And unfortunately, in hydraulic engineering, we don't have the same requirement. And one of the challenges that we have, and we need also to look at the other side, is that it's very difficult in particular to have field observation in hydraulic engineering. And hence, we are in a situation where the validation can usually only be restricted to small size physical model. And there's always a problem, even if you validate against a laboratory model. Can it still be extrapolated to full scale?
Okay, and so there are sensitivities issues as well, like you don't know what the physics are that really you need to be sort of capturing appropriately.
I mean, let's put it in a slightly different context. Most laboratory models in hydraulic engineering are performed with a Reynolds number between 10 to the 4 to 10 to the 5. A typical spillway in operation operates with a Reynolds number of 10 to the 7 up to 10 to the 9. That's nearly 4 orders of magnitude greater. And that is clearly a major challenge.
Tushar, you had a question?
Yeah. Hi, Hubert.
Yep.
I'm Tushar, a PhD student from University of Melbourne. And as a young researcher, I actually found the first part of your talk quite interesting, where you talked in detail about, citations and how you publish and all. So with this reference to the slide number 11, I guess, where you gave a distribution about single authorships and collaboration and all. So I just had a small question regarding when you publish along with collaborations. So you showed some concerns on that. Well, I thought that if you publish with collaborations, there is a good chance of having a very quality output. So can you share your thoughts on that?
Okay, so look, this is a tough question because it's related to both the number of authors and the type of co-authors that you have. There are certainly, as an editor, there are certainly more and more concern of submission with too many co-authors, 6, 7, 8, 9, 10 authors, where sometimes you wonder whether the contribution of all the co-authors is worth to warrant authorship. It's also something that is of a concern to promotion committee and academic appointment committee, where something which is not always said is that when you start to have more than 3 authors on a paper, we might not consider this as one of your publications unless you are the first author or the first author is your PhD student and you are the second author. Simply because being the last author in a long list of authors doesn't mean much. Now, of course, having some good collaboration with people that you respect and people that you can trust can be beneficial in terms of your own personal and professional experience. But my comment here in relation to this slide is that co-authoring with an international person for the sake of co-authoring with someone internationally based is not going to increase your impact. If you have a very good colleague in your university or in Australia, the quality of your work could be even better than trying to find someone overseas.
Okay. Yep. Thanks for that.
Madhukar has a pretty granular question, if you'll pardon the pun, in the group chat. Do you want to explain your question, Madhukar, or?
Sure. Thank you. First of all, thank you very much for your talk. I'm trying to validate a CFD model using the volume of fluid finite volume method, specifically the interform solver of the OpenForm package. And I'm comparing my results for a pipe flow with the steady normal results in your books. And I'm seeing 15 to 20% difference between the CFD results and steady normal flows. I'm using the RNG K-epsilon model, which overpredicts the speed and underpredicts the water height. With the standard K-epsilon, the results are in better agreement, and I'm using the roughness wall functions. So is there any clue on how the results can be, CFD can be brought into closer agreement with the usual results for normal flow?
Look, it's not an easy question because the quality of your validation is going to be linked with both the quality of your experimental data set and the quality of your numerical modeling. And for this, you clearly need, at the first place, in terms of looking at a physical data set, to have a physical data set that is detailed enough to be able to truly compare with your CFD model. I mean, I'm going to take an example. If we look at the velocity in a steady open channel flow in a rectangular channel, most of the literature will only give you the velocity profile right in the middle of the channel. Now, when you have a flow which is in a rectangular channel, you will have some sidewall effects. And what you would need or what you should use is data set where you will have vertical profile at several transverse locations. You also need to have some data set which can provide you some very very detailed information very close to the bed. Something which is not as trivial, which is certainly more difficult in a water channel compared to the wind tunnel. And one of the challenges in CFD is that, one of the challenges in CFD of open channel flow is that for a given flow condition, you have potentially two unknowns. You have both the position of the water surface, which is unknown beforehand, and you have the velocity. So altogether, there is a lot of parameters that you need to get it right. And I'm not completely surprised of what you are describing. It's quite usual not to be able to get directly some good fit. But I think in this case, what I would recommend you is to select a data set that you can rely upon, particularly a detailed velocity data set.
Okay, thank you.
Did we have any other questions for Professor Chanson?
I have a question if no one else does. Thank you very much for the talk. It was very interesting. We're sort of getting a flavor of a lot of different things in fluid mechanics from these four seminars that we've had in the past month. I had a question. So in your conclusion slide, there was some reference to field measurements, I think. And I remember seeing a talk by, I think your colleague, Professor Richard Brown, about Lagrangian data assimilation in the Brisbane River, if I'm not mistaken. So I'm wondering if you can perhaps comment on some of the work that's being done to combine field measurements with CFD modeling of these complex flows.
Oh, tough one. And I think the problem is difficulty on the safety in doing field measurement in large system. So let's take, for example, an example like the Brisbane River. The Brisbane River is a very wide river, which is nearly 80 meters wide in some places and 5 to 10 meters deep. And if one would like to get a detailed three-dimensional characterization of the velocity field, you would need probably to block the Brisbane River and have a series of instruments which can record not only the velocity, but also the velocity fluctuation simultaneously at different points. This is clearly not possible. And we are therefore have some data set or field data set, which are either very coarse. So for example, using an ADCP or a current profiler, we can get the velocity profile at almost at different time, but within a few minutes at different location, but no information on the velocity fluctuation or any turbulence characteristics. Or you need to deploy a few instruments at a fixed location that you sample at high frequency, for example, 200 Hertz with some of the ADV, for a relatively long period of time. Again, when we talk about a system like the Brisbane River in Brisbane is a tidal river, so the flow direction changes twice a day with the tide, and hence you need to do some relatively long duration, high frequency data set, which instead, in turn, bring very large data set, although they are only point measurements. So the challenge there is that in a system like the Brisbane River, it's extremely difficult to characterize everything at once. If you were going to take another example, which is, for example, the water jet of the Three Gorges project, you saw the photograph earlier in the slide. I would love, as a multi-phase flow person, to do some air water flow measurement in such a water jet. But clearly, it's too dangerous, and no one is able to do any measurement there. So I think with the field data set, the problem that we have is that our field data sets are, first of all, very rare. And when they are there, when they exist, they are usually very limited, even if they are of good quality.
Thank you.
Sai, you had a question?
Yeah, hi. Actually, this is probably kind of a weird question because I'm not much aware with the fish locomotion. I'm actually a PhD student at Monash University in mechanical engineering. This is kind of like why did chicken cross the road kind of question, because I was looking at your talk and I was interested in you discussing about fish having to expend a lot of energy when crossing the culvert. So I know salmon and some other kind of fish travel upstream, but is it like a general phenomena that fish travel upstream the river, or if you could just comment on that?
Yes. Okay, so I think here fish traveling along a river is a natural process. But depending upon the species and depending upon the family or the guild of fish, you will have different behavior. You are going to have some fish who are going to migrate for spawning and reproduction. Some will migrate downstream and will reproduce at sea. Some will migrate upstream and reproduce inland. You have also, most of the time, especially when we talk about small fish, a simple migration of habitat. So basically the fish are simply trying to move to find different places, different sheltering places. And even in terms of the small fish for their reproduction, they will tend to migrate in response to a flood. So very often there are some triggers that are not always fully understood, but for most of the Australian fish, they will typically be the rising limb of the flood. When the flood starts to take place, the discharge starts to increase. The fish start to feel that there is an increase in flow in the river, and they will start to use this opportunity to migrate, often upstream, sometimes in the downstream direction. So generally speaking, in terms of habitat, most of the fish will tend to migrate one way or the other between their own natural habitat. And every time you have a culvert, which will block this natural passage, you are going to affect adversely their habitat or eventually their numbers.
Okay, yeah, thanks a lot. This is like the hydraulic equivalent of why did chicken cross the road. Thanks, Hubert, for an amazing talk.
On a related question, Professor Chanson, I would imagine naively over time that the culverts just build up with sediment around the corners and kind of slowly aggregate towards a parabolic type geometry. Is that it? Is there something cheap and nasty that can be done to sort of break up the geometry of the culvert to keep the boundary layer, you know, to have a nice slow boundary layer for the fish to swim alongside?
Look, sedimentation in front of you on the bottom left-hand side, you have an example of massive sedimentation of a culvert. Sedimentation is something that is unwelcome in a culvert. As a professional engineer, irrespective of fish passage, you don't want sedimentation because this is going to reduce the discharge capacity of your culvert. And usually, provided that your design is sound, you will find that in the barrel, in the narrowest part of the culvert, you have usually large velocity, and this large velocity will basically reduce the risk of sediment deposition or sediment accretion. So generally speaking, with a properly streamlined culvert, sedimentation is not a major issue.
Okay.
A greater issue, however, this is something that is to some extent relevant to what you mentioned, a greater issue is debris. So when we talk about a box culvert in relation to fish passage, we find that the bottom corners are the ideal place for the small fish to migrate. But when you start to have rocks, branch, large debris which start to block the culvert or possibly block these bottom corners, you might be in a situation where the structure can no longer be fish friendly. And unfortunately, there's not much you can do except, as you can see on this bottom photograph, bring an excavator or bring some people to clean up the culvert.
Do we have any other questions for Professor Chanson? Okay, well, I think we would all like to be at a point where we have enough citations to be able to do statistical analyses on our publication records. It's probably a bit of a ambitious aspiration for certainly myself. But yeah, so thank you very much, Professor Chanson, for a very interesting and wide-ranging talk. And we hope to see you all next Wednesday.
Thank you very much, David. Thank you, everyone.
All right. Thanks, everyone.
Bye.
Bye.
Thank you.